So today we're going to learn about, again, resonance and standing waves. And resonance occurs whenever conditions are right to build a standing wave. So we talked about standing waves before, where you have a node and you have an antinode, you have a section where you have constructive interference, you have a section where you have destructive interference, and hopefully you remember some of that stuff that we learned before we went on break. So resonance is going to occur whenever conditions are right to build a standing wave. Here in this example, since they had the same frequency, then the conditions were right to transmit that energy over. So we did have a resonance situation. When we added that fun tack, then it became too heavy. The resonance situation was gone. It didn't match anymore. So, yeah. The resonant frequency is the frequency that corresponds to a specific standing wave. And there's only a few frequencies that can achieve resonance or can produce a standing wave in any given setup. And this will all make more sense as we're going along. But there's a frequency that goes with each wave, because again, frequency equals speed times wavelength, or frequency equals speed over wavelength. V equals f lambda. So there, for every given wavelength, there's a frequency that matches it. So if we have a standing wave that has a certain frequency, then there's a wavelength that matches that also. So we have a resonant wavelength and we have a resonant frequency. And again, these are all the ones that make a standing wave. So the fundamental wavelength is the smallest wavelength portion that can make a standing wave or that can achieve resonance. And if you remember back in the day, we learned that whenever our ends were closed, we formed a node when we made a standing wave. But when the ends were open, we made an antinode. Remember the little wavy thing that we had up here? And when we had a clamp down, it always formed a node when we made a standing wave. And when if it was unclamped, if it was open, then we could form an antinode on that. And so that will lock us into position. Whatever blew in last night, my body doesn't like. You killed it, man! Ow. Okay, what did I do? I rubbed on it, which means I added some energy. Do you hear every frequency imaginable? No, you're hearing one that's making a standing wave in this thing. How come I can hold on to it, but when Aaron touched it, it died? Because I'm holding it where? At a node. If I'm holding it at a node, then right here it's vibrating big over here and it's vibrating big over here, but in the middle it's just pivoting. So if I'm holding it right at the pivot point, I don't kill it, but if I hold it at the antinode, it dies. Well, what happens if I hold it at a different spot? Then I force a node. If this is going to work at all, it'll only work if a node is where my hand is. So I come over here, and notice we switch to a different sounding wave. So we have a different frequency that matches this length. And again, I can hold on to it here, and it's okay because both of these are nodes. So I can grab it here and here, but if I touch it in the middle, if these two are nodes and in between them is a antinode, so now this became the antinode, so when I touched it here, it killed it. But when I held onto it here, not so much. You can get a really strong standing wave in that thing.
What is it?
Those are called singing rods. Because they're rod shaped and they sing. Okay, so yeah. Everybody have all that stuff written down that you need written down?
No.
Good. A guitar string. How many people have seen a guitar before? Here is one. So if you've never seen one before, now you get a chance to look. Down here the string is clamped down. And up here the string is clamped down. So both ends have to be clamped down. So are they going to be open or closed? They're clearly going to be closed. So what has to form at both ends? A node has to form at both ends, which means in the middle we're going to have a antinode. So this thing, as it vibrates back and forth, is like one big antinode. So this was like the smallest wavelength we made out of the big spring when we made the standing wave, and it just looked like you were going to play jump rope. So that's what normally happens when you do this. But reality is when you make this wave, that is the dominant wave, is the one that's there. But the other one where you have a node in the middle and we have two nodes and we have a bunch of nodes in there, those are all happening at the same time. And the ones that happen at the same time that aren't the dominant one is the one that you hear, that's going to be the fundamental. The other ones are called overtones. And they are happening at the same time, but they're not happening as strong. But we can force that to happen. So anyway, the fundamental here is going to be one wavelength because we're going to have half in between there. So, yeah, I think you'll be able to see that. No, you won't. Never mind. So we'll just switch to here. If we have our guitar string, if it's clamped down at both ends, then we have to have a node at each end, and we have to have a antinode in the middle. But is that the only thing that can form there? No, the only thing we know we have to have at both ends are two nodes. Now I know I have to have one antinode in between the two nodes, so this is the smallest one that can happen. So this one is going to be the fundamental wavelength, because that's the smallest one that can make a standing wave. But I can always make a standing wave as long as I know I have a node at each end. Well, I could also have another node in the middle. So I could have that situation happening. And so I get a node in the middle, and of course I'm going to have antinodes in between them. And so this is going to be my first overtone, or the first harmonic, depending on who you talk to. And that will be the next wavelength portion that made a standing wave. And again, anything will work as long as I have nodes at the end. And so I could have one end in the middle, or I could have two ends in the middle. And of course, in between every node has to be a antinode. So this is going to go up, and then that one's going to go down, and that one's going to go up, or vice versa. And we could end up with this. This would be the second overtone, or the second harmonic. And so it's going to end up looking like that. Well, again, if I have a crest or a trough here, then this is how much of a wavelength? This is going to be 1/2 of a wavelength. And here I have both a crest and a trough, so this is one wavelength. And this has a crest and a trough and a crest, or a trough and a crest and a trough, so I have 1.5 wavelength. And by now you guys should be smart enough to say, hey, I'm noticing a pattern here. The next one in the pattern would be, and then, so it clearly we're just jumping by 1/2 a wavelength bigger every time. And so the ability to see patterns, that's good. That means you can think. So, yay, team. We like that. So this is the way the pattern runs. And so when you're playing your guitar string, as you hit this, this is the note that you're hearing, but this note and this note are also there. You don't hear them as strongly, but they're still there. But you can force them to happen. Just like when I grab this thing, when I grabbed it here, well, a node wants to be where my finger was, and when I moved it over here, a node had to be here, and so I had to change everything. And so you can do the same thing with the guitar string. If you measure out the string from clamp to clamp here, the middle point is right here. So if the string is already vibrating and I smack it right in the middle, what do I force to form there? A node. So if I force a node to form, then what happens is I'm going from 1/2 of a wavelength to one wavelength. So if my wavelength just got twice as big, then my frequency just got, I'm sorry, the wavelength actually got, this would be a whole wavelength. My wavelength just got half. I have whole wavelength now in the same space that I had a half a wavelength. So now the wavelength just got 2 times smaller, which means the frequency will get 2 times bigger. And yesterday we learned when we double our frequency, we jump by 1 octave. So what you hear is the string jumps up 1 octave when I hit that middle point, because now I forced the node to be at that point. I jumped up to the first overtone, which is exactly 1 octave above that frequency. Isn't that cool? You can also just kind of hold it a little bit, but not all the way down. When you pluck the string, and you'll still get that same. So it'll jump up an octave. Kind of fun, right? My guitar skills are almost as good as my piano skills were. We can have some of you serenade us later.
La la la.
Yeah. So that's the way it works with a guitar string. Now, is a guitar the only thing that we can play?
Yes, this is true.
No.
Play
All
bands.
stringed instruments are going to work on that same principle, but strings aren't the only type of instrument. Well, we also have this thing, and I know you don't think that this is an instrument, but it still was making noise, right? If I'm holding it in the middle, then the middle is a node, but both ends were open. So what formed at both ends? Antinode. So we could also, instead of like a guitar string where both ends were closed, here we could have a tube where both ends are open. And if both ends are open, then an antinode has to form at both ends. And what has to be in the middle, of course, is a node. So here I'm going to go from a crest down to a trough, or from a trough up to a crest. And so again, if I would chop this in half and bring this piece over here, it would look exactly like the fundamental of the guitar string did. So that still means that the fundamental here is 1/2 of a wavelength. And again, if my only condition is my ends are open, they have to be antinodes at both ends, I could have another A in the middle, which of course means I have to have ends in between them. So I'm going to go crest to trough to crest. And you say, that looks like DNA. No. And again, if I would chop off this bottom piece and bring it over here, you'd say, hey, that looks just like 1 whole wavelength, which it would be. So the first overtone, and you say, hey, I'm smart enough to figure out after only 2 examples that this is the exact same pattern we just saw, right? So what we're noticing is that if both ends are open or if both ends are closed, it doesn't matter which, we're going to go from 1/2 to 1, 1/2 to 2, 2.5 to 3, and it's going to jump like that. And this is going to be the standing wave. So this is the situation we had with the little singing tube here. When I was holding onto it in the middle, I was forcing the node to be in the center, and we were shaking here and here, so I was in that situation. But when I grabbed it over here, I was forcing a node to be here, which is why I could also grab it over here, because that was also a node. But then when I touched it in the middle, now suddenly that middle part is an antinode, and I killed it. That makes sense? So it's almost like matching reality or something. So we end up with situations like this, but we also have a third situation that we could set up. Instead of both ends closed or both ends open, we could have 1 closed, 1 open. So what happens if we end up with something that's closed at one end and open at the other end? Well, what has to form at the closed end? A node, and the open end has to have a? Now, do I have to have anything in between these two? No. So the node would be like here, and it would be either going to a crest or it'd be going to a trough. So this, compared to that, looks like, hey, that's half of the half, which means my fundamental would have to be 1/4 of a wavelength. But again, that's not the only standing wave I can make in here. I know I make a standing wave if I get an antinode and I get a node, but I could have another A and another N in there. So if I shove Nana into a tube, she's not going to be happy, but I would go from node to node and down, and it would end up looking like that. It's a thing. So again here, if this part was, from here to here was 1/4, right? And then I say, hey, if I chop that in half, this piece looks just like that piece, and this looks just reversed, so it looks like I have 1/4 and 1/4 and, hey, that looks like there's, what do you know? The first overtone is going to be 3/4 of a wavelength. So anybody astute enough to pick up on how big of a jump that is? Yeah, if I go from 1/2 to 3/4, that's 2/4, which is the same as 1/2 wavelength bigger. And what was the jumps in all the other ones? Half is still going to be a half. We're just starting at a different spot here. So now we're going from 1/4 to 3/4 to 5/4 to 2/4, or you can say 1 1/4, 1 3/4, 2 1/4, 2 3/4, whichever way you like to say it. But that's going to be the jumps like that. So that's the way that's going to work. Now you're saying to yourself, okay, this is interesting, but what does this have to do with reality? I'd like to show you that. Imagine for a minute that we have a tube that's open at both ends that's 85 centimeters long. What we're saying then, in theory, we can only produce certain frequencies with it. We can't produce every frequency under the sun. We can only produce certain frequencies. So if we start filling out this chart, we say, hey, if this is 85 centimeters long, how much of a meter is that? That's going to be 0.85 meters. Is going to be the length of my tube, but what's going to fit inside that tube? Well, if the tube is open at both ends, then the fundamental is going to be how much of a wavelength? If both ends are the same? Yes, it's going to be 1/2 of a wavelength. And so we're saying 1/2 of a wavelength fits inside this tube. So we're saying 1/2 of a wavelength is 0.85 meters. That make sense?
Yes.
But is that the only thing that fits in this tube? No, the fundamental fit in there, but we could also fit in the first overtone, and we could fit in the second overtone, and we could fit in the third overtone, and we could fit in the fourth overtone. And the overtones keep going, but we're going to stop there math-wise because we figure it out. But what was our jumps that we were always going to jump here? By half. So if we start off at 1/2, the next one's going to be 1, the next one's going to be 1.5, the next one's going to be 2, the next one's going to be 2.5. But those are all going to fit in that same tube length, which was 0.85 meters. So I can fit half a wavelength in there, and the next standing wave that could fit in there would be 1 wavelength, and the next one would be 1.5, and the next one would be 2, and the next one would be 2.5. We could also make a wave that is 1 3/4, but would it make a standing wave? One that's 1 3/4 would not make a standing wave because it wouldn't have an antinode at both ends at that point, so it would mess everything up, and it wouldn't make any noise that we would hear. We only hear the ones that make a standing wave. So now what we have to do is figure out, well, how big is a whole wavelength? Well, to do this, we pretend this is algebra, and we solve for lambda. I'll do the first one for you, or the second one for you. 1 wavelength equals 0.85, so 1 wavelength equals 0.85. Woo! That's tough math. Okay. In the first one, is this 2 at the bottom or at the top? This 2. It's on the bottom. So if I were to move it to the other side, it would be at the top. So it's going to be times 2. So 0.85 times 2 is going to be 1.7. I can do math in my head. That's good. Okay, the next one, to get lambda by itself, I need to divide both sides by 1.5, right? That would give me lambda. So now I'm gonna break out my friendly calculator. My mental capacity is gone now. And we get 0.56666666. To get this one by itself, of course, we want to divide both sides by 2. So 8's going to turn into a 4, 5's going to turn into 2, 5. I can do that one with my calculator. And then the next one we would divide both sides by 2.5, and we get 0.34. So now we got to go to that really, really, really hard equation that I learned you the other day. V equals F lambda. Here we're looking for, hey, we're looking for F, so I need to move the lambda down yonder. And you say, hey, I have all the lambdas right here in this column. If only I knew what V was. Oh yeah, yesterday we learned that V is going to be 343 over whatever the lambda is. So we're going to stick in all these lambdas into that equation. So 343 divided by 1.7 gives me 202 hertz. Hey, what do you know? So this tells me that if I have a tube that's open at both ends that's 85 centimeters long, I should be able to produce these 5 notes. But would I produce other notes? Only higher ones that match this pattern. Could I produce something that's like 300 hertz? No, because I can't make 300 hertz make a standing wave in this tube. Only these frequencies will make a standing wave in the tube. So these are the ones that are going to make a note that I can actually hear. Now, here I have for you a tube that's open at both ends. Guess how long it is? It's about 85 centimeters long. What do you know? It's like magic or something. So what I'm going to do is I'm going to take this thing and I'm going to start to spin it around. When I spin it around, that's going to force air to move through this. Now, if you look at it, it's full of ridges. And that ridges mean that air is going to hit that ridge and some of the air is going to bounce back. And so we're going to have a lot of random compressions and rarefactions happening inside of here. So if I have millions of different compressions and rarefactions happening inside of here, how will I know which one I can hear? Only the ones that make a standing wave are going to be the ones that I can hear. And which ones did we say should be able to make a standing wave? 200, 400, 600, 800, 1,000 should be around the time where we hear this. Now, I cannot get this to spin slowly enough to get the 200. But that one's about the 400. Did I get a broken one? No, what happens is these things get abused by you guys and they start to crack. And once they start cracking, I may have to get another one. Yeah, let me grab another one. That's probably not.
So that's what that is. I always see like everyone I got. Yo te cansé. I always see these videos turn it like how
Like when I was a kid, I would always get them right. Not always.
She was spot on 30.
Yeah.
gonna try a pink one. Okay, so that's the 400, that's the 600, 800.
Make a song.
So, do we hear every note imaginable here? No, we jump distinctly from one jump to another, which is, hey, what our theory said should happen here is that we should jump in distinct jumps here. We shouldn't be able to get standing waves out of those other frequencies. Now, how can we tell if I'm lying to you and these aren't really those numbers?
Might that be a machine that you have on your desk?
Hey, maybe we could like hook it up to the computer and actually read this and see if it works or something. So, we'll see how well that goes. Yeah. No, not that one. Where'd the other one go? Why are you disappearing? You're killing me, Smalls.
No, it came out.
Where?
It was up for a second, but then it disappeared.
No kidding.
You're so.
Weird.
Oh, God.
Okay. Gotta love that. Okay, well, apparently we'll try and resuscitate that in a second. But, has anybody ever played a musical instrument before?
Yeah.
What if this was curved like this? Then I could make notes out of it, right? But could I make every note possible out of this? No, I can only make the notes that can make a standing wave in here. So we do have an instrument that's curved like that. It is called a bugle.
Oh.
And a bugle is, you can make a bugle long and skinny, but it kind of gets in the way and you smack people in the head when you go by. So we curve it around like this and it makes it nice and long. And what happens is you put your mouth at this end where there's a mouthpiece and you try and make random noise on this end. For those of you who have never played a brass instrument before, it's beautiful. You put your lips next to the mouthpiece and you go. That's what you do, seriously. So all you're doing is making random vibrations. So random vibrations go in, but what comes out on the other side are the notes that make a standing wave. And again, in a tube of that length, there's only a couple that can make a standing wave. So if that bugle happens to be that length, then I could pop out that 200, that 400, and that 600, and that 800, and if I was really windy, I might get out that 1,000. And that would be like the frequencies that I could produce with this. But that's it. That's all I could play. I need an instrument that I can change. So then you invent the instrument that's called the trombone. And in the trombone, you've got a section in here that you can stretch that way or back this way, which means basically I've made my tube longer or shorter. When I make the tube longer, what's going to happen? The wavelength is going to get bigger, so the frequency is going to get lower. And so it'll make a lower note when you stretch that out and a higher note when you stretch in, because again, there's going to be a standing wave that matches each of those lengths you go to. If I don't want something that I can slide back and forth, they have things called trumpets. And trumpets have 3 little valves in here, and they have lots of extra little loops of instrument here. And every time you push down on one of these levers, it diverts the air around another way. And so you basically, every time you push that, you've made it longer or shorter. So when I can make 3 notes out of with the fingerings up, I push this one down, I got 3 different notes. I push 2 of them down, I got 3 different. So all these different fingering positions, I have all these different notes that can be produced by that. Is this all starting to make sense?
Yes.
It's almost like there's physics behind musical instruments too, not just math behind the music and all that fun stuff. That is so weird. I don't know where my fingers are reaching. So, try one more time for the magic thing to appear.
Oh, that stinks. What time is it?
Give it flowers.
Okay, that was really odd. Well, we'll find it in a minute. Of course, for tomorrow you want to
Work.
do problems B.